So today we're going to look at the GKR Prover again, but this time it should be faster, right? Because of I've done one pass already. So any questions, just let us know. Let me share screen first. Oh yeah, what's the question? When you went?
Okay, so I said that when we're coding the circuits,
Yeah.
someone to test, you have to create like a hard-coded kind of
Circuit. Yeah.
now to passing the input to my values.
Yeah.
So I know that we can actually, that's not how it works, but kind of hard-coding circuits, like, so how does that work?
You always outcode circuit.
You always hard-code circuits. I thought somebody wasn't trying to say something about producing a circuit that, something like that.
And that was like hard coding, but you're coding from a different layer of like abstraction. Like a circuit is directly related to like a program, right? So it's just now where are you writing that program? You can write it on the circuit layer, or maybe you can write it on just like second layer, or some other, or Rust layer. By the end of the day, you always prove a very specific circuit. You get. So you could write something else that can compile down to your circuit representation. So someone will now write in that higher level language. Does it make sense? Any other question? Alright, let's start. So we have a circuit, we have a prover, we have a verifier. The prover evaluates the circuit at a given input, and then the prover wants to convince the verifier that that evaluation was correct. So before we can do anything, we'll need to get some polynomials from that circuit. And then that will now be what we'll use to perform the proving step. Okay? So this is an example circuit. Right? So let's say the input is 1, 2, 3, 4, 5, 6, 7, 8. And then the operations are plus, 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 times, plus, plus. So what will be the output of the first gate? What is the second one? What is the next one? Last one? This one? This one? And this one? So these are the intermediate evaluations, right? So we have the input layer, we have the I'm putting input layer. So every layer has an index, right? An ID that you can use to identify each layer. So this layer could be like layer 0, right? Then this one is layer 1, this is layer 2, and layer 3. Now for each layer you need to generate, not for all, but you need to generate the WMLA, right? So the WMLA just represents the evaluation at that layer. Okay, so you need to generate like W0, which is basically just a multilinear polynomial that just has like 88 inside, right? So if you evaluate this polynomial at 0, you're going to get 88. So this polynomial has just let's write the bits. This is 0, right? This is 0, 1. This is 0, 0, 0, 1, 1, 0, 1, 1. This is 0, 0, 0. Right? So this is a polynomial that has just one input. That's all that is required to specify the. Now this other one is going to be a polynomial that is in that has like 21 and what, right? So this is the W1 polynomial in a single bit also. Then we have a polynomial here. This is W2 of I'm not going to write everything again, but you get the idea. So this is going to be 2 bits, right? So that's a A1, A2. Cool. So the values are 0, 0, you're going to get 3. Values are 0, 1, you get 7. And another like that. Hope it's clear. And then finally, the input layer, W3, has 3 bits. A1, A2, A3, right? So your values are 0, 0, 0, you're going to get 1. Values are 0, 0, 1, you're going to get 2. On and on like that. So this is the first set of polynomials that we generate. So your circuit implementation should have a W function or whatever you want to call it. But the goal of that function is that it takes in a layer ID and it returns a multilinear polynomial corresponding to that layer, right? But this will only work after you have like evaluated it. So what you could do is you could pass in the evaluations, then to just like pick it from there or something, depending on how you want to do it. But W makes sense, right?
So the evaluation as a layer, so that means we're putting this evaluation here as though it is the evaluation form
of a multilinear polynomial. Yeah. So that's why it's important that you can get to your evaluations out. Okay, so
is it at the layer level or at the circuit level?
It's at the circuit level.
Circuit level. But then in the circuit level, the evaluation of the circuit is returning multiple.
Yes.
So are we going to return another, like, is it going to be for each of them? Okay, you say you are going to receive an ID.
So you give a layer ID, and that will know the evaluations I should use, then to just return the multilinear polynomial. Okay. So now that we have the W poly, the next thing we need to encode is the relationship between two layers, right? So there's a polynomial here that represents this relationship. But this polynomial depends on 2 other polynomials, 3 other polynomials. We already have one, but 2 other polynomials. That's the Adai and the Molai polynomial. I'm just blitzing through, so if you have any questions, just interrupt. So here we're going to have add 0, right? How many bits is A? What of B? What of C? So we are going to have 2 polynomials of this form, right? Now the add 0, what inputs must it take in before it can evaluate to 1? 0, 0, 1, right? That's the only Boolean. Does that make sense? That's the only Boolean input that it can take to get a 1. Any other Boolean input will give it 0. What of mul? There's no input, right? So there's no mul gate there. Cool. Now what of next layer? Add 1. How many bits is the output?
1.
B.
2.
2. So that will be 1. B2, right? Then the second one, C. That's also 2, right? And then the mul just takes the same form. So what would we need to pass into the add to get 1? Yes. Does that make sense?
Yes.
Why are we not echoing it together?
Yes,
It's 1, 1, 0, 1, 1, right? And that's the only one that will give you a 1. What of the mul? 0? Yes. And that's the only one that will give you a 1 also. So that's all for like layer 1. Then let's move to layer 2. So we have add. How many bits is the output? 2 bits, right? That's A1. A2. How many bits the left? That's B1, B2, B3, right? Then C1, C2, it follows the same. Then we have more 2 similarly. Cool? Now what would we need to pass into the add that will give us a 1? Wait, how many things are we going to pass into the add that will give us a 1? 3 things, right?
Yes.
So the first one is what? Okay. Then let's look at the more. How many things are we going to pass in? Okay. And it is what? Okay, cool. Now what of add 3? Is it add 3? There's no add 3, right? Because that one doesn't have any up. Make sense? So now, what we need to do next is to create the FBC polynomial. You have a question? Yeah.
What we are trying to do is specific for
What do you mean?
this guy. What if we don't know the number of bits we have, number of layers?
You will know that. You have already defined your circuit, right?
So when we implement, we already know the circuit we want to do.
You will create something that can allow you to create any circuit, right? Right? Like your circuit structure should already like know how many. I don't know how to put it. Yes. So obviously your circuit implementation initially is not going to know anything about the concrete structure, but it knows how to get that information. So when you now have like a specific instance of your circuit, also like this, then you can now get like the concrete values for anything you want to get, like the number of gates and all these things.
I think it's 5 layers.
It should still work.
Just by the 5 is this model.
What model? Like see. This adds 0, right? You should be able to get the number of bits in add 0 by looking at the number of gates at layer 0 and looking at the number of gates at layer 2, at layer 1, sorry, right? Once you know those two, then you can know the number of inputs.
Like can we implement n number of
Layers.
Gates, layers?
Yes.
That is what we are also.
That's what you ought to do. It should be generic. Just needs a way to be able to get like the relevant information. We'll still do. No, don't worry.
Sorry.
Yeah.
These guys
Yeah.
on the right hand side,
Yeah.
they are the FBC polynomial.
No, they are the ingredients. These are the add and more.
Okay, they are just the add and more.
Yes.
Why this one is a W?
Is it W? So with all this now we have the
Don't make
ingredients and we can now make the FBC polynomial. Make sense?
Yeah.
It doesn't make sense for some of us. What does it make sense? That's what we'll talk about next. Yeah. But do you understand the pieces? Yeah, no, you're required to implement your circuit first. Right? Your circuit doesn't use this yet. It's when you want to start proving, that's when you start using all of this.
So the combination of the W polynomial and the add and more is what leads us to getting the FBC polynomial.
Yeah. So the FBC polynomial has an ID too, right? This polynomial here represents the relationship between layer 0 and layer 1, right? There is a relationship between layer 0 and layer 1. So that means with this, you can get the output of any node at layer 0 using just the W1 polynomial. Like only using the W from layer 1. So let me use like FABC. So this is the general formula, right? So you have Fi of A, B, C, right? It's going to be equal to the add I on that same layer of A, B, C times what? W on the next layer, right? Of B plus W on the next layer of C. Then plus the mol I right? Makes sense? So this is a polynomial that can check for, so layer I, right? That's layer I is 0. So you pass in A, B, and C. This A, B, C represent candidate indexes, right? So you're saying A is my output, then B is what I think the left is, and C is what I think the right is. So what this polynomial would do is that it's going to check that layer. Is there actually a gate connection that has A as the output, B as the left, and C as the right? If it exists, if it does not exist, it will return 0. If it does exist, then to figure out what that A node is, like is it an addition gate or is it a multiplication gate? Are you listening? This FABC polynomial, right? It takes A, B, C, like candidate labels, okay? And then it does checks, and it does something. So the first thing it does is that it first of all checks that such a connection exists. So like now, if it's 0, right? The only connection that exists at layer 0 is 0 for the output, 0 for the left, and 1 for the right. So the only thing that will make this actually do anything is if you pass 0, 0, 1. If you pass any other thing, it's always return 0. So the first thing is to check is that there's an output node on that layer that has the label 0. Then there's a left node on that layer that has the label B, right? The output has label A, left has label B, and then there's a right node to that output node that has label C, right? It's just looking for that like A, B, C connection, okay? Then if it does find that connection, what it's going to do now is that it's going to figure out the type of gate that A is, okay? So if A is like an AND gate, then it's not add the values of B and C and return that to you as the output. But then if A is like a multiplication gate, it's going to multiply those two values and return that to you as the output. Does that make sense?
Yes.
Sure?
Yeah.
So that's what it does. Yeah.
So, in that Fi into ABC,
Yeah.
A is the output of
Yeah.
the gate,
Yeah.
B is the left
Yeah.
input, C is the right
Yeah.
input.
But not the actual values, the index. Yes. So you now use this WI
Yeah,
to get the actual values.
actual one.
Yes, but that's just the index. Makes sense?
So even the A is the index.
Yes, A is the index of the output. Makes sense?
We use WI to get the actual
WI plus 1 to get the actual value. Yeah, you know the WI plus 1 represents the actual values on every layer. So the B and C are just like the indexes. So we get the actual value by just evaluating this at the index. Make sense? Alright. But the problem now is that this formula doesn't actually know what your circuit looks like, right? So if you tell it that, okay, I want the output for A, let's say A was 0, it doesn't know what the actual left is and what the actual right is. But we have a formula that can tell us if we have found the right thing or not, right? So what we do is that we check all possible values of B and C. So let's assume now we wanted a formula that can tell us any outputs at Wi, right? We're going to make use of this to search. We'll fix A to this A, and we're fixing the outputs. Then we're trying every possible value of B and C. Only one of them would work, depending on how your circuit is. But for what we have done so far, only one of them will work, right? Because there's only one left, and there's only one right. When that works, we're going to have the actual value of the output, right? So it's like it tries everything. Most of them will be 0, the other one will be 0, the other one will be 0. Then it's going to get to a point where it actually finds the right thing, and then to get what? 88, right? So at the end of the day, the output will be 88. And then that's going to be like the evaluation of Wi of A. So this formula is actually, Wi of A is the summation of BC in the Boolean hypercube when you evaluate Fi of A, B, C. Now there's no A here, right? Because of A has already been fixed by this Wi of A. So this entire thing will be partially evaluated at A. So you just have a polynomial that is just BC. And then you now evaluate this over the Boolean hypercube for BC. So what you're doing is that you have said that, okay, the output node is 0. You have fixed it, right? And then you're now trying all possible combinations of left and right nodes. So you start with 0, 0. So this thing will now go and check. Is the left node to this output 0? And is the right node also 0? The answer is no, right? So it's going to return 0. But it's a summation. So it will go to the next one, right? Which is 0, 1. Is it 0 and 1? Yes, it is, right? Then it's now perform the add, which will give us what? 88. So now at this point we're like 0 plus 88, right? This was 0, 0, this was 0, 1. Then for 1, 0, is the left 1? No. Is the right 0? No. So it's going to return what? 0 also. And 1, 1. Is the left 1? No. Is the right 1? No. So it's also going to return 0. So when you sum everything, I'm going to get 88, which is exactly the same thing as evaluating this thing at what? 0. Does that make sense? We sure?
Explain again.
I don't understand it.
This
I'll explain it.
W polynomials are just the evaluations, right, of that particular layer. Scroll down. This Wi of A, it's another representation because
Yes.
this Wi of A is a formula for what is this Wi of A? Let me just
Wi of A is like, we're saying that there are two ways to, you know, you already have a W polynomial for every layer. We're saying that there's another way to get
the W polynomial.
the W polynomial by using the W polynomial of the next layer. So you can see that this Wi, right?
Yeah.
And this Fi, right?
Yeah.
Still same layer.
Yeah.
But if you look at the Fi, you are seeing that it's using Wi plus 1,
Yes.
which is the layer under it.
Yes. Yes.
So we're saying that there's a way to get this Wi evaluation by only using Wi plus 1 evaluations. Does it make sense?
Yeah.
I can explain again.
This Wi equals.
So what?
I know that Fi is polynomial representing a layer, right? What's down Wi?
No. Wi is the evaluations at a particular layer, right? It's the same thing as all these your W polynomials, right? So W0 is 88. W1 is 2167. Yes, that was the evaluations. So now we're saying that we can get the evaluations another way, right? We can get it by using the FBC polynomial. Okay?
Sorry, It's not always going to be like one value. Because you are looking for W of 0 and I get it. If you are looking for W of it, just get two values.
W1, you still get one value. Because you're always fixing.
You have a polynomial.
Yeah, but you fix A. You fix A.
Yeah.
A is the output gate.
Okay, then you have to have.
So, if you choose A as 0,
Okay.
you get 21. If you choose A as 1, you get 67. That makes sense, right? So, should I go over the how we got the 88? Okay. Yeah, it sense.
So what we are doing here is like, okay, we know our W polynomial
Already, yeah.
already.
We got it one way.
We got it one way.
Yeah.
But now there's another way of getting W polynomial, which relates with the previous layer, with values of the previous layer. So what we are doing now is, instead of using our W polynomial
That was
know,
given to you by the.
we now substitute that other formula for the W polynomial of that layer. So if you pass in the right value, it's going to give us back something that will give the W
So
polynomial.
basically, it's polynomial identity testing. We're trying to check if two polynomials are the same using Schwarz's lemma, right? So it's like the Wi of A was given to us by the prover, right? Not really given, but there's a Wi of A that was gotten by the prover, right? By just going through feed forward. Then we're saying that there's another way to get that same polynomial, but we relate it through some check. So if the prover was honest, left side will be equal to right side. And then we now test that relationship using some check. And then we just continue that process. So usually it's like there are two ways to do something. And then you're trying to check that the two ways give you exactly the same thing. That's what most of like ZK usually is about. Does it make sense?
Yeah.
Vaguish.
So while you explain this thing, what came to my head, or it's kind of out of this world. Yeah, that's actually what came to my head, like proving like, that where we have P1, V1, proving that voice law is related to first time distance. So
Yeah,
like you have
both
P1,
sides,
V1
yeah.
and first time distance. When you now substitute like P, which is pressure, like force over area, then you now start cancelling it. It's the same thing like first time. So you're just substituting this guy over this place.
So two ways to get the same thing, yeah. Then you can use short zippers to just test it once rather than testing it everywhere. Okay. Let's do. So let's assume we're working with W1 now. Right? W1 is actually 21 and 67, right?
Yes.
So now we already have the let's say we already have the W1 polynomial. We can evaluate at 0 and get 21. We can evaluate at 1 and get 67, right?
We didn't find out W1 polynomial.
Whoa, the prover did now.
Okay.
Yeah. But relax. The point now is that we're not even looking at prover verifier right now. The point is just like there are two ways to get the same thing, right? So now what we want to do is we want to express one of these outputs as a function of the next layer, right? So what we're going to do is I want to evaluate W1 at what? Let's say at 0.
So where A can either be 0 or 1.
Yes, in binary. But then obviously you can evaluate it anyway. That's the Martina extension. So let's assume A is 0, right? What is the output supposed to be? 21, okay? But now we're going to do it step by step using the thing from under, right? So we're going to be using the F1 BC, right? F1 of 0, BC. Does this make sense? Which is the same thing as the add 1, right? Times W2 of B plus W2 of C, right? And plus the mol 1 W2 of B times W2 of C, right? So what happens? We will start, we're evaluating the entire BC, right? Now for W1, the BC is what? No, it's 2, 2. Right?
Yeah.
Makes sense? Okay. So A has already been fixed. So all the add and all the moles, they don't have A anymore. So it's just B1, B2. So what we do is that we're going to iterate over all possible 4 bits representations, right? So we're not going to do everything. So if we start with 0, 0, 0, right? What's happening? We're basically looking for. So the output has already been fixed as 0. So we're only looking from the point of view of this guy now, right? Then we're trying all possible values of B and C. And we're seeing if we find the one that actually matches the circuits. Okay? So we'll start with 0, 0 for B and 0, 0 for C. This gate now, does it have 0, 0 as the left?
Yes.
Yeah.
But does it have 0, 0 as the right?
No.
So that entire thing will evaluate to what? 0. Right? That's the first part of the sum. We'll get a 0. That's for 0, 0, 0, 0. Then next time we're going to try for 0, 0, 0, 1, right? So, does it have 0, 0 as the left?
Yeah.
Does it have 0, 1 as the right?
Yeah.
Then it will now look at the gate. And then it will now do like, it will evaluate the W2 at 0, 0, which is what? 3, right? And evaluate W2 at 0, 1, which is what? 7. Then to perform the gate operation, which is multiplication, right? That's 3 times 7, which is 21. So that's what it's going to return as the output for this. Okay? This, what I just did was what this function is doing. Because when you put in 0, 0 and 0, 1, the add gate will turn into what? A 0. But then more gate will remain a 1. Then it will now do the multiplication. So I just did it like directly, but this is what the formula is technically doing. So we have 21 now. Now, regardless of what we try going forward, they will all be zeros, right? Because for the like the next thing is supposed to be like 0, 0, 1, 0, right? But then the right gate is not 1, 0. We already know the right gate is 0, 1. So every other thing will be 0 except for the actual correct left right label. So when you now sum everything, you're going to get what? 21. And that was exactly the same thing we were supposed to get when you evaluated it at what? But we only used W2 to get that answer. Does that make sense?
So, instead of having to sum everything, I want to just say once you see something like above 0, just
Are we sure it's only going to be 1?
Exactly.
We are sure of that.
No, I'm not sure of that. Depending on your circuit. GKR allows you to. So it's possible to have something that looks like this. You have one gate, right? You have a left, you have a right. But then at the same time, you have another left.
Nah, I don't know.
The thing is that you're going to restructure our picture.
If you want to do something like this.
Yeah.
No, everybody that is using output index can technically do this. All you need is like 2 gates having the same output index. Yes.
That is so
Why would you want to? You can you can express
Index,
you can express more complicated. So right now you can only do A plus B
Yeah.
and A times B.
Yeah.
Now imagine if you had something like this. You had a gate here. It's so hard to explain. But imagine like A, B went together, right? So you have A, B. Then let's say, it's so hard to explain. What it actually looks like, let me draw it the way, this is not how it's, it's still fun in 2 gates. But you can do some interesting things with it. Like the power of adder and multiply is not yet like, you guys are not yet harnessing it to like the highest potential. But imagine we had this and this, right? And then you had this, okay? So let's say you had A here, you had B here, you had C here, you had D here. What does this represent? This is A plus B, right? Plus C, D, right? You can do this in just one gate. Gate. Yes. So you have
So you think the output of this
Now the one gate can do both
Well,
addition
it's,
and
That gate is a custom gate, man.
Not really. It is, but not really. Like you're doing, there's a way to do addition via interpolation.
Does that mean like it's like you're trying to get the value of the alphabet
Yeah.
out going through that?
It's had 2 layers. Yes.
That's what maybe something else.
Yeah, so you're just going straight A, B, C, D. And then you now get out A plus B plus C, D.
As the output.
Yes. So the way you do this is that you have an AND gate, right? I don't know how you guys represent your gates, but let's assume you had an AND gate, right? Your left is A, right? Your right is B, right? Your output also is 0. And your operation is add. Then you have another one where your left is C, your right is D, your output is still 0, and your operation is multiplication. So how you guys are doing it now is that you now say your result index your output is equal to the whatever. Instead of doing equals, you can do plus equals. Do you get? So when you do plus equals, the first one would change the 0 there to A plus D. The second one will now add CD in there. And you can have as many as you want like that. And it's all just going to that one.
So that means we're not supposed to use that equal to, we're supposed to use equal.
If you want this level of flexibility. Only if you want this level of flexibility. But it's not compulsory. Do you
I
get?
think it's better.
Might be trade-offs. Does it make sense? Does it make sense? Where were we? And so someone was asking like, yeah, it was Dean. You were like, so we're showing you a reason why you cannot just stop when you get something that is non-zero. You could technically, if you know that your circuit can never have that double output thing. Right? If you know you can never have that, then you can technically stop once so that you don't have to do like the full evaluation. Okay, makes sense. We sure?
But this W1.
Yeah.
So just putting that label to 0, 0, 0. So it looks like you're doing all the possible
Combinations of B, C,
yeah, but you're only going to have
1, depending on, yes. And then that will give you the output. Makes sense?
It's like you're removing a layer.
Technically.
So if you have like 4 layers now, can we do 1 layer?
It could, technically. But there are trade-offs. There will be trade-offs. Are we good? It is. For now. So we confirmed that the problem was the fact that it went off. So I was also recording on Meet. So when the light went off, both of them stopped at exactly the same moment. And then even on Meet. But that was because I was the only one on the. Usually Francis was supposed to join the call too. Then both of us are there. But when I'm the only one there, I think for some reason it just stops sharing my screen. Like, why are you sharing your screen to nobody? That kind of thing. When something happens. OBS, I think once this thing disconnected from the monitor, OBS got really confused. The Meet might have stayed. Yes, OBS would have stopped. But Meet would have been there. But now Francis is on the call. I hope. Yes. Okay. Are we good?
Yes.
Now let's prove. nothing happened.
Scroll up a little. Yeah, here. What we are evaluating is
Bruh. Okay, let's prove. So we'll do the proving protocol. This is how we started, right? Both the prover and the verifier had a circuit. The verifier did not want to use that circuit directly, right? For whatever reason.
sorry. Okay. Scroll up. Please finish this line. There's something missing.
Which line?
That W10 equals to 0 plus 21 plus something is missing.
Plus 0 plus 0 plus 0. The rest of them are zeros. Yeah, there's only one gate. Does it make sense?
Yeah.
Sure? Like it's only 0, 0, 1
Okay.
that would make this 0 pass, right?
Yeah.
Because that's 0, 0, 0, 1. Any other combination of B and C would never result in a gate that has output 0 on that layer.
But we are on W1.
Yes, this is W1.
So you only did the evaluation for the first gate.
Sorry. This is W1, right?
Yes.
And then we did W1 of 0.
But only W1 of 0.
So we're fixing this already.
Okay.
So now we're trying to find the BC that fits with this,
Alright.
which is only 0, 0, and 0, 1.
Alright.
What was the W1 of 1?
So W1 of 1 will fix this, right? Then the only time that we'll get a value is when BC is 1, 0, 1, 1. That's when we'll get 67. But the rest of them will be plus 0 all the way.
I have a question.
Yeah.
Is it so compulsory that we have to perform the evaluation or check over every other combination? Because it is clear and glaring that this gate is for X and so on is going to be so positive question and this one is for multiplication. Why do we have to? I know that, but why are we doing this?
It's not clear to the formula.
It's not clear to the
You're trying to create one algorithm that works on any circuit, right? So it's clear based on this circuit, right? But there could be another circuit that has a different way of writing the gate combinations.
Okay.
So that this formula that we have described here works regardless of the actual circuits, right? So the actual circuit is kind of like encoded in this add I and more like MLE.
This W by W we're trying to get here, right?
Yeah.
Are we trying to get it so that we can now use it in the output there? Right?
This WI of A. The WI of A is using this FI of A. The point of this is that at some point we're going to have a claim about WI of A. I want to reduce that claim to a claim about WI plus 1 of something. Right? You know the point of GKR is to reduce claims until you get to the input. So, and this is sum check. You know, when you do sum check, at some point you're going to get random challenges for this guy. And this guy is made up of WI plus 1. Okay? So the verifier will be able to get the add I and the mul I. So the only thing the verifier won't be able to get is like the WI plus 1 and WI plus 1.
Yeah, exactly.
Yeah.
So how do you evaluate this?
So the prover will give you that, and then you just continue the reduction. But we'll get there. Make sense? Okay. Proving. So the prover verifier, they had the circuit. Same circuit. Then the verifier gave the input to the prover, right? Saying that I want you to evaluate the circuit on my behalf. Okay? The prover does that. If we're in a trusting society, the prover will just tell us what the output is, and we're done. But the verifier does not trust the prover. So the prover needs to somehow prove that 88 is indeed the answer. Okay? So the first thing that the prover sends is the output polynomial. Remember that the output could be more than one value. So the prover sends the output polynomial, which is what? W0 of A to the verifier, right? Now, once that has been sent, the verifier will sample a random challenge from the field and send it to the prover. Right? Right? Then once this is done, the prover and verifier will now evaluate that W0 of A at R. That's where they'll start the protocol from. So let's call it, like in the book, M0, right? M0 is equal to W0 of A at R. Okay? So basically, they're just trying to create a random claim about this W0. But you don't want the prover to know the claim initially. So that's why you make the prover send you W0 first. So he has already finalized all his entries of W0. Because if he knows it, then he can modify W0 so that it will fit that R. So once you have sent it, then the verifier will just sample a random point in the field. And then this is like a claim, right? This is a claim. Now we need to prove that this is correct. So the problem right now is that the verifier doesn't trust this W0, right? It was given to him by the prover. The only thing that the verifier trusts is W3. This is W3, this is W2, this is W1, this is W0. Any question?
I'm looking at the
Okay. So, how do you prove that M0 is equal to W0 at R? Yeah?
So, when the verifier sends a random challenge
Mm-hmm.
to the prover,
Mm-hmm.
what the prover does now is using that random challenge. So, we're doing evaluation at W1 at at 0. So what the prover will do now, will now substitute 0 with the random challenge,
Substitute A with R.
which is in that
In that
example,
example,
is 0.
yeah.
So with the random challenge.
Yeah.
Now, okay.
Good? Alright, let's continue.
So,
Yeah.
in a situation where the reason is just like I know the reason when people don't have to,
Yeah.
but in this situation is one
Yeah.
and A being R will not affect
Potentially. So we don't even know. I know some people had issues with that last time when they were implementing, but it's until we start implementing before I would know. So one thing we could do is that rather than just having it as just one value, we could have it as index 0 of a line, right? So it's now be like 88, 0, for example. So that we just expand it to, rather than being a constant poly, to be like a one variable poly, right? So you write at 0 to be 88, you write at 1 to be 0. But I think you should still be able to work with 88 directly. But I've forgotten, so until I get into like proper implementation before I remember what's happening. Yeah.
So if the prover substitutes the random challenge at A in W1 into A, so you substitute that guy there. Now, and we got that Wi of A is equal to summation of Fi into A, comma B, comma C. So the A in that summation will also change to that random challenge.
Mm-hmm.
But the B and the C remains the same for that particular
Over the hypercube.
gate, over the hypercube. Okay.
Wait, let's continue. So W0 of R is equal to M0, right? This is what the prover claims is the case, right? Because the prover just gave us the W0 and we evaluated at R. So this is the claim, right? It's a claim about the output polynomial. And in GKR, what we want to do is we want to reduce it to a claim about the next layer. So we want to get a claim or claims about W1, right, from W0. Okay? So we started with this. Now, there are two ways to get a certain value at W0, right? We could do it like direct evaluation of the W0 polynomial, but we could also use the FBC polynomial. So this W0 of R could also be written as the summation, right, of F0, R will replace A, right, BC, where BC is summed over the Boolean hypercube. Does this make sense?
Yeah.
This makes sense, right?
You said there were two methods.
Yeah, the first one is just evaluating W0 at R, right?
The second one is
Getting W0 from the FBC polynomial.
What is the advantage of one
zero
over the
plus
other?
There's no advantage of one over the other. You just need two ways to get the same thing to make sure that both of them are consistent. Because this other one is given to you by the prover.
Okay.
No, the prover was the one that sent W0 to you, and you don't trust that. So you use
verifier will now do this one.
both of them will now engage in some check protocol.
Okay, verifier will do his own some check protocol separate. Prover will do some check.
It's program. Some check is an interactive. It's like
and verifier. Okay.
so they will do their part of it.
So you're saying that first one is just the one who got sent.
Yes, you know the prover just sent to W0 of A. The only thing that the verifier has is W. Wait, W0 of A means that it's a polynomial that has just one variable. A is like X, right? R is a field element, so that you are not trying to evaluate W0 at 2 or 3 or something. Yes. So the only thing that the verifier has is W3, right?
Yeah.
That's the only thing you trust. But now the prover gave it W0 of A. And then the verifier now sampled a random R, which is a concrete field element. Now, the prover is claiming that if you evaluate W0 at R, you're going to get M0, right? These things are field elements. So this is like a field element, and this is also a field element.
The prover claims that if you validate that R,
Yes.
gets M.
Yes.
What's M0?
M0 is just a random value. That's like when you evaluate W0 at R,
Yeah.
you will get,
So this is after you have already sent that it.
yes. No, which is it? The output, yes.
Is there a name for M0?
M0 is the claimed sum,
The new claim
is the evaluation of the output at R. Like if you evaluate the output at 0, you're going to get 88, right? So now they gave you like the verifier chose a random value, not just 0. So whatever that evaluates to, that's M0. Does that make sense?
Yeah.
But now you can't trust this, right? Because the verifier could have given you any W0. So what you want to do is you want to somehow reduce this claim. So this is the claim. This is like our first claim. This is our first claim, right? We want to reduce this claim to a claim about W1. Does that make sense?
Yeah.
So that we can keep on doing that until we get to a claim about the inputs. And then we're done. Give me a sec. All right. Okay, so the prover sent W0 of A.
What is 88 in this way?
88 is W0 of 0.
Oh.
Which is like the output, technically. So you know the verifier knows how many gates or how many outputs are on the how many outputs is expecting. So the first output will be at 0. Then if it's expecting another one, it will be at 1. If it's expecting more, then it will be the first one will be 0 0, then 0 1, then 1 0, and on like that.
Sorry, the output, are you saying the layers now?
No, the output of the entire circuit. Yeah. Yes. Depends. In this case, it depends. That's what we're talking about. So it's either like it's going to be just a polynomial that has like 88 inside, which is a constant poly, or we might be forced to put like a 0 to make it a. So if it's 88 now, evaluating that any R doesn't really matter, right? It's always going to give you 88, but I can't remember. So I have to like check or do something. But I know that some people had issues with that thing. Okay? Your question was answered now. Yes, your question was answered. Okay. So we evaluated W0 at R to get M0, right? But then we don't trust that. So we're going to get that same M0 another way using some check. Wait, let me go forward. We're going to get that same M0 using some check, okay? So this W0 of R can be written as F0 at RBC, right? Right? Because we said W I of any A is written as Fi. So we just replace A with A. And with R.
But will it fit into
No. Wait, all your question.
So I'm trying to mentally get what's happening.
You want to mentally get what's going to happen?
No.
Or what
So
we have talked about so far?
So this is it.
Yeah.
Is it. So it will help us get the pattern.
Sure.
So the prover has proven all the stuff he wants to prove.
He has evaluated it.
Output,
And everything is
and
output.
has given to the verifier.
He gave it to the verifier.
Now, what the verifier is trying to do is, the verifier will generate a random challenge to be like evaluated at that W0, which will give like a corresponding output.
Yes.
Right?
Yes.
So at the end of the day, the verifier will continue generating random challenge for the prover for each of the layers or for each of the gates. So what the verifier is trying to do basically is, if at the end of the day, after generating all those random challenge, the final equation, like the last layer, is able to give what was at the output, automatically he agrees that everything the prover did from the final layer to the output was correct.
You're missing the details, but so it's not the only random challenge that the verifier generates is this one.
Only this one.
It's only this one. Every other thing is derived from this one through some check. Because some check itself, and maybe you could think of it as like, okay, maybe the verifier is still the one giving the random challenge in some check, and that's fine. But let's just go step by step. All right.
My question is, now that we are putting this random challenge into this,
Yeah.
would that still give us
M0.
for this gate now we have let's say the new company that we are using numbers.
Yes. Why the putting back here? So we'll do exactly what we did when we did that 0 plus 21 plus blah blah blah. Okay, let's proceed. Let's proceed for 5 minutes without any question. Then after that, we can ask questions. Okay. So when we're done with the first sum check, then we can now ask questions. Okay. So now we have W0 of R is supposed to be equal to M0, right?
Mm-hmm.
We don't trust that. So we want to verify that using sum check. So we already have a way of writing any evaluation at the top layer as a sum of something in the bottom layer. So we just do that. So they said W0 of R is equal to M, right? So that means this W0 of R is supposed to be equal to what? M0. And M0 is supposed to be equal to the summation of F0 at R. R has already been partially evaluated, right?
Yeah.
So we can just have like BC, right? Then we now do BC is in 0, 1. If the prover is honest, this would be correct, right? And this is exactly like a sum check problem. The M0 is the claim sum, and then the F0 of BC is the polynomial that we're doing sum check on. Okay? So what the prover and verifier, so at this point, once you have like your claim and you have your FBC polynomial, you now invoke the sum check protocol that you have already written. You invoke that to now perform like a sum check proof. Okay? So this will basically look like this. You now have like prover, a smaller prover, right? Still a prover, but a smaller prover, like P sum check, PS. And then you have V sum check. So what's going to happen is that the prover is going to send what? The initial claim sum, right? And it's also going to send F of what? B. He has partially evaluated C over the Boolean hypercube. Sum check, you always leave the first variable and then you sum the rest of them over the Boolean hypercube. So send the claim sum and then F of B. Then the verifier would evaluate F of B at what? 0? But F of B at what? 1. And this should be equal to what? M0. F of 0. And yeah, let's call F of B. But does it make sense? So once this is done, the verifier will now sample a random number, right? Call it R1 from the field. And then it gets the next claim sum, right? Which is going to be F of B evaluated at R1, right? So this is going to be the claim sum for the next round. So it sends what? R to the prover. Then the prover is going to now evaluate that F of BC, but replace B with R. It's going to say R1. Make sense? So the initial poly that the prover was working with was this like F of BC, right? So you're going to replace this with R1. This is just sum check. Yeah, so we're now going to get F of C. And then this is what it sends back to the verifier. Verifier evaluates F of C at 0, plus F of C at what? 1. And this should be equal to, let's call this M01 or something. Should be equal to M01, right? Right? Then once F of C and of X. X. Just like a variable. Yeah.
FB of R1.
Yeah.
What's the verifier and the prover does it?
The prover doesn't need to do it.
So it's only the verifier.
Only the verifier needs to do it. Like the prover doesn't use the claimed sums other than the first one. But is this making sense? No, it's just like after you send R, what does the prover do? The prover will evaluate, replace B with R, right?
Yeah.
Leaving just C. So this is going to be like an F of C poly, right? But normally you're supposed to now sum the rest of them over the Boolean hypercube. But there's no rest. There's no rest now. That's like if you had F of A, B, C. In sum check, at some point you get an R for A, right? So then you'll be left with F of B, C. But then you're supposed to sum C over the Boolean hypercube so that you can get F of B. This is now what you send over to the verifier, right? Then at some point the verifier will send you back another R. So then you now have F of R1, R2, C, right? Which is just F of C. there's nothing left to sum over the Boolean hypercube. So you just send f of c. Does it make sense? So f of bc is what we started with. Then the verifier sent r1, so now we're left with just f of c. But then I just moved the c down as call it f of c, and then I put x. These two are equivalent. Does it make sense? The reason why I did that was so that when I'm writing like this, you can know that it's still f of c. But you can just see, if this is better, you can use it like this. Does this make sense?
Yes.
So at this point, the verifier would now also sample R2 in F, right? So they can perform the oracle check. So it's going to do F, evaluated at R1 for B, R2 for C. It's supposed to be equal to F of C, evaluated at R2, right? This is the oracle check. Now it knows what this is, right? Because we gave him F of C, and it can easily evaluate at R2. Cool? But it now needs to evaluate the initial poly at R1, R2. Does it make sense? Where are you confused?
Probably because I was right. So, can you just go through this sum check process?
Do you get the sum check problem? You get this one,
Yes.
right?
Yeah.
Okay. So, all you're just doing is you're just running sum check on F0 of BC with a claim sum of M0. What we call trauma response. Okay. So, how does it work? The prover is supposed to send the claim sum and the first round poly. The first round poly is just f of b, right? Because we started with a poly that is f of b, c,
So the provider is supposed to send the claim sum and the first
and the round poly in sum check now.
round.
Like if the poly was, let's say f of a, b, c, the provider is going to send the sum
And
f of a,
and the poly, the first poly.
f of a.
Yeah.
Yes. So this one now, there's no a starting, right? The first variable is b, so it's sending f of b. Makes sense?
So f of b is the main initial polynomial.
No, the main initial polynomial is f of bc. The same way the same other one is f of abc. The initial polynomial, you can think of it as like public. You still put that one into the transcript.
Okay.
Like a sum check proof is like, it's just what the claim sum and the round polys. The round polys are all univariate polynomials, right? So the first univariate polynomial here is f of b. Does that make sense?
The reason why I'm asking is because our sum check process is you commit the initial polynomial and the claim sum before you start generating the round poly. So now if you are going into sum check in this case, what would be our initial polynomial? We know our claim sum.
You cannot have an initial polynomial
Okay.
because of the verifier does not know w. So you know that this f0 of bc is the same thing as add, right? Right?
Yeah.
That's what it is. So if you want to pass the initial pool, you need to send this entire thing, right?
Yeah.
But then the verifier doesn't have access to.
With
He only has access to the. Wait. Run charge. He only has access to the input layer,
yeah.
which is W3. So the point now is that your sum check can no longer
Taking the
initial poly.
That's the point of modification.
That's why we say you have to modify your sum checks. Makes sense? Because we cannot put that in transcript. Yeah, because it doesn't know it. Cool?
Yeah, continue.
Any questions?
Sorry, please.
Hmm?
Sorry,
Yes, it is.
when the most check.
Sorry, like, I'm sorry.
No.
Like, what are we passing to the verifier again? I need to get it.
What are we
If
passing
you are
to?
no more passing the normal initial pull to the verifier, like that type of F0, what is it?
It's a round polynomial.
Is it
The prover still knows the FBC polynomial.
Okay.
So the prover will still be able to generate the round polys. That's the FB and the FC.
We just send it to the verifier. Okay. Continue.
I need you guys to see like the big picture, to see the full end to end. Cause right now it's like you're just seeing pieces and it's still confusing.
So W not of R.
Yeah,
R is like a fixed value.
yeah.
When we had the sometimes it's 0, sometimes it's 0, 0, 0, 0. And that will determine what's your BC in 0, 1.
Yes.
Super, something.
Yes.
But in this case,
R is random. It's not. It's not in 0, 1.
0, 1 always. But at some point,
No.
so
R.
as far as
R is anything from the field. And so the way multilinear extension works, right? The way just like Lagrange and all those things is that when you evaluate them at Boolean, right? The result is usually like 0 or 1. But then when you evaluate them at a field element, the result is now cannot be a field element itself. Do you get? So that behavior, that add I and mod I, the fact that it only gives you 0 or 1 only exists when you are working with bools. But when you start working with bools, it can now give you also any value from the field.
So if you were doing like W1 of R,
Mm-hmm.
if I go to do that,
Yeah, what is that?
so if you were doing that, we used to be
R is any random number from the field. Okay. Yeah, BC is always 0, 1. They are summing over the Boolean hypercube.
Always 0, 1.
Yes,
Like
in
when
this.
we're using A or normal stuff, it was 0, 1, this power 2 now. Let's say we're represented as a placeholder yesterday.
Mm-hmm. And when you are going down, the length of B will increase.
Exactly.
You know, you can see that your W polynomials are starting to use like B1, B2, C1, C2. So each one of them is still 1 bit, but now you have 2 Bs. So that's the only thing you're partially evaluating is A. Then B and C are, the rest of them are from the Boolean hypercube.
Okay.
I feel like I'll say again.
Where are the sum check?
Yeah,
Yeah.
but I feel like people might have lost track. Okay. Prover sends W0, right?
Are we doing good?
Prover sends W0 of A.
Yes.
Verifier sends R in F, right?
Yes.
Then prover and verifier evaluates it at R, right? So you get M0. Doesn't trust this. So you need to do some check to prove it. So M0 is equal to summation of F0 right? Where B and C is coming from the Boolean hypercube. This is a sum check problem.
Yes.
M0 is the claimed sum, and then F0 of RBC is the initial volume. Now you have a sum check problem, you can invoke the sum check protocol. So you invoke it here. You now have the prover and you have the verifier again. Now the prover is going to send the claimed sum and it's going to send F0 of, or FB, F of B, right? Because this is partially evaluated R, so that one can technically disappear. So you just have like FB. Make sense? So keep B a variable, sum the rest of them by B and pack it. Then it sends f of B. Verifier evaluates f of B at 0 plus f of B at 1, right? And that should be equal to the claimed sum. If it is, the verifier now evaluates this at a random, so the verifier samples a random R, right? And then evaluates this f of B at R to get the new claimed sum. That's a C2. Then the verifier sends this R to the prover, and then the prover what? Sends, yes, evaluates the initial poly, replacing B with what? R1. So this will give us what? F of C. Then the prover sends back f of C to the verifier. The verifier evaluates f of C at 0 plus f of C at 1, and it should be equal to the claimed sum that it generated at that time. Yeah. Then once it's done with it, it picks a random R again from the field and then does the oracle check. So, give me a sec. Hello? Yes. Yeah, sure. Okay. So we now have the oracle check, R1, R2, right? So f of the initial poly evaluated at R1 and R2 is supposed to be equal to the last round poly evaluated at R2. Does this make sense? The verifier can get this. This will be what? Let's call it C3, right? It's supposed to be equal to f of R1, R2. Now the problem with this is that the verifier does not know how to compute this, right? Because of this is technically made up of the add, R has already been evaluated, so it's supposed to be like BC, right? But we already replaced BC with what? R1, R2, then it's times W what? So W0, right? So that will be W1 of R1 plus W1 of R2, right? And plus the mol of R1, R2 times W1 of R1 times W1 of R2. Now, both of them have the circuit. This add and this mol is in the circuit. So that means that the verifier can compute this and this. So we'll call it A, R, and M, R. These are concrete field elements. Okay? They are multiplying this with W1 of R1 plus W1 of what? R2. And times W1 of R1 plus W1 of R2.
That M0, R1, R2. Is that what you're supposed to do? After that step, we're supposed to do the oracle check, right?
The oracle check is the last step of some check.
Like that point where it goes F0, R1, R2.
That's the oracle check.
You said we can't do the oracle check.
And we're trying to do the oracle check, right? We're showing why the verifier cannot compute F0 of R1, R2
Inside the sum check.
without help, yes. Thank you.
Okay, so from here, when sample random challenge.
The first one,
Yeah.
this is R1.
Here's the number of
Where is the C1? Yeah, like, why is there C2 and there's no C1? No, C1 is just like M0. That is just a claimed sum in some check. This is just some check. The initial claimed sum was M0, right? I could have called it C1. Then when the verifier evaluates the univariate poly at the random challenge, it's getting the next claimed sum.
That's the three is like
C3 is the last claimed sum.
last game.
You know, every round of some check, you're going to get a new claim sum for the next round. So the first one was M0, the next one was C2, and the final one is C3. The final one is the one that you're not going to use in the oracle check. Okay? But the problem right now is that normally the verifier usually has the initial poly, and the verifier evaluates the initial poly at all the challenges to get the other thing at the side and checks whether it's equal to C3. If it's equal, then it's correct. But the problem right now is that the verifier does not have W1, right? And W1 is what was used to make F0. So that means that the verifier cannot actually evaluate F0 at R1 and R2 without help from the prover. But the verifier can evaluate add and mol because they both have the circuit, and add and mol comes from the circuit. So that's what I did here. This is a field element. This can be like 5 or 6 or 7.
Like normal addition.
Yeah?
You just very add it.
That's what?
Let's say you have 5 and 7. You just add it.
Yeah, but it doesn't know what this is yet.
No, I'm talking about the AR.
Yeah, it just computes. It knows what the polynomial is, so it just evaluates at R1. No, it might not be 0 and 1. Because R1 is no longer in 0 and 1. Yeah, so it might give you like a random field element. Okay? So, the problem right now is that we have W1 of R1 and we have W1 of R2. It was repeated here, right? So really what the verifier doesn't know is W1 of R1 and it doesn't know W1 of what? R2. And because of it doesn't know this, it cannot compute this full thing. So it cannot know this. And because you can't know this, you cannot complete the oracle check. Yeah.
So you said that it's not compulsory that the result of add R1 and R2 is not compulsory.
Yes.
So how would I know you put it in
Yeah.
how would I be able to evaluate for other field elements? How would I be able to evaluate that as is it the 1 and
Yes. Yes. So like if add was let's say 0 and 1, right? The actual polynomial is going to be what? 1 minus x times 0, right? Plus x. Technically, right? So at the end of the day, this will reduce down to what? X. So if I already at 0 or 1, you'll still get a boolean. But if I already at something like 5, you're going to be getting 5. No, you get. It's a multilinear extension. If you play with it in the boolean space, your answer will still be boolean. But if you play with it outside the boolean space, your answer will no longer be boolean. How does the verifier know? Know what? Because it's in the circuit. Like when you are done with your circuit implementation, just looking at your circuit, you should be able to know what the add MLE is and what the mod MLE is. Because we can see like the addition gates, you can see what it's connected to. And both the prover and the verifier have the circuit. So both of them can come up with the polynomial.
Just the evaluations that the verifier doesn't know.
Yes, just the evaluations. So the verifier has the entire circuit, but it doesn't want to run a particular input on the circuit. Does that make sense? So that means the verifier is able to compute add at R1, R2 and mol at R1, R2. So you now get field elements, right? But then it doesn't know this and it doesn't know this. So you cannot yet compute the full thing to check whether it's equal to C3. Cool? So what happens is that the prover now gives the verifier the evaluation of W1 as R1 and the evaluation of W1 as R2. Okay? So it gives him directly. So it says that, okay, W1 at R1 is equal to O1 and W1 at R2 is equal to what? O2. Okay? The GKR prover. Yes. It can still lie at this point. If it couldn't lie at this point, then we're done. Once we check that it's equal to C3, then we're done. If we assume it cannot lie at this point, so once it's done. So the prover just tells us what W1 of R1 is and what W1 of R2 is. Then we just replace it here. So AR times O1 plus O2, right? And plus MR times O1 times O2. All field elements now, right? So we're supposed to get a new value. And hopefully that value is also C3, right? So that when we now do the oracle check, C3 is equal to C3. And then we are done with the first round of GKR. It's not as complicated as this. It's just because it's so step by step. It's just get your claim sum, just call sum check dot prove M0 and initial poly. Finish. You're going to get your sum check proof out. Once you get your sum check proof out, you're done. You go to the next round.
So,
If you are implementing GKR, the best is the class doing.
It will be GKR related implementation design-ish classes.
so we're going to modify our sum check.
Yes.
So,
Not take an initial poly.
yeah, and to take in W1 and W2. So just W1. W1 evaluated at R1 and W2. W1 evaluated at R2.
Those are two different sum checks. What do you mean the
You know, we are not going to change it. Okay, I believe it's based on implementation because since we are not doing the oracle check,
yes.
so what I'm not saying is when we are doing
When you are verifying.
when we are verifying,
Now you are returning a bool, right?
yeah.
Now you're no longer returning a bool. You are returning C3. You are returning what the oracle check was supposed to evaluate to. And then you're also returning. I think that's all.
So we have to talk about
You have to do some check. But we'll do all those ones when we want to start looking at implementation.
Okay.
I need you guys to first understand the theory. The steps are they look too much because of your mental model is not yet solid. No, now.
we get.
The mental model is not
It's not an insult. You get what I mean, right? Sorry. Everybody will understand it at some point. Okay. So now, oracle check, right? C3 equals C3. We're good. Okay? But then the prover gave us two things that we cannot trust like that, right? He told us that W1 of R1 is equal to O1 and W1 of R2 is equal to O2. So now it's like we're restarting. You know, at the beginning we had W0, what was it? W0 of R is equal to M0, right?
Yeah.
That was the claim. Then we did all of this just to reduce it to something about W1. Now it's like we're doing it all over again. We'll reduce it to W2. Then we'll do it all over again. We'll reduce it to W3. But at that point, the verifier has. So if you tell it that W3 is equal to W3 at R4 is equal to 07, it can check this, right? It just evaluates its W3 polynomial at R4 and checks whether the answer is equal to 07.
So that one, that oracle check is not even the main thing.
The oracle check, no, it's not the
The
main.
oracle check just confirms that you did the actual.
The correct,
whatever.
yes. It's just for that round, exactly. But it's trusted, yes. So that's the problem. Normally, you're not supposed to. You know, the first one we had just one claim, right? But now we have two claims. So what we're supposed to do is there's something called a 2-to-1 trick, right? you take two things and you convert it to just one before you now proceed, so that you don't have a blow up. Because if you do one here, there will now be 2, 2, then it's now be 4, and then you're just like going like that. Yeah, it will be 8, so it's just ridiculous. So there's a 2 to 1 trick. I cannot even dare to teach you guys the 2 to 1 trick right now. It's this is a 2 to 1 trick. I'll send this to the group. You guys should attempt to understand it. Yes. So this is alpha, and then this is beta.
Might surprise you.
That's the hope, right? No malicious intent whatsoever. So we'll just black box the 2 to 1 trick now, alright?
So when you go that 2 to 1 trick, what did you say you want to say to us?
The,
That 2 to 1 trick.
yes, the page.
What resource was that?
No, we wrote it.
Oh yes.
Not that we created it, though.
And you
We understood it, and we now wrote it. Yeah.
So the whole
That
resource
page,
contains
yeah.
Just that page.
That's my notes
Yeah.
on Obsidian.
Wow.
Yeah.
Okay, the other things are other things that you
Which other things?
you had the content.
Oh, yeah, that's our other things. Yeah. Okay. So we'll black box it.
You don't
Wait, oh,
publish
I hope.
these notes.
Alright.
Why not?
PTSD.
Which PTSD?
Because of what happened yesterday. They always check it if it's true.
Oh, okay, yes.
But you could publish them.
Oh, understand. But I get what you mean. I know. Yeah, I just set me up.
Do not despise your days of little bit.
Okay, so we'll have 2 to 1 trick. So rather than doing 2 sum checks, alright? Because this thing here, right, can be represented as W1 of R1 is the same thing as the summation of F1 of R1 BC, right? But then this F1 is going to be using W2 under the hood, right? But then you now do the same thing here, right? But instead of R1, you're using R2. So that's like 2 different sum checks. And then that will reduce to 2 claims each, which is 4 claims in total. So we don't want to do that, right? So we use the 2 to 1 trick. So the 2 to 1 trick will basically take these 2 sum checks and create a new one for you. So instead of O0 and 01 and 02, it's going to be like 03, right? A new value. Then that's going to be equal to W. So basically, I'm going to say that W1, still W1, evaluated at, let's say, R3 is equal to 03, right? But if this one is correct, then this will be correct, and this will be correct. Does that make sense? So now you only need to check just one. That's where the,
Is this
that's the 2 to 1 trick.
is it composite?
What's composite?
Like composite, you have a function, you have another function, bringing them
Oh, no.
It's not composite.
It's more like random linear combination.
Random linear combination.
What does that mean?
That's like you take two things, you take two things, and then you combine it linearly by scaling it by a random factor,
What do you use to do that?
alpha beta. So it's
Alpha,
like
beta.
you have
Is it like linear combination?
it's like linear combination.
Linear combination.
Yeah. It's like doing the dot product of
Two vectors.
two things. So this is alpha beta, then this is like your sum check 1, sum check 2. So you now do like alpha times sum check 1 plus beta times sum check 2.
So where alpha and beta are
They are random points. Then at the end of the day you have like a new sum check, which is sum check 3. That somehow like makes use of everything. But you need to now go and look at the details. This one is just like a high level idea.
Alright.
Okay.
You see this of writing and understand.
Yeah, you should already understand it now.
When the math equal, that is just basic.
You guys understand it. But we'll explain it at some point. But you guys will understand it. So
So after we get our we first check something before we continue.
check what?
So first check if two things are equal.
No, I said that if this is valid, maybe we have some check or whatever, then this is valid and this is valid. I'm just showing that the reduction is linked. You get? So now that we have compressed like this, we're now at exactly the same point we were when we're talking about W0 equal to M0. You get? So it's just a for loop.
So is this I'm trying to relate to what you said this that we have that proven argument
Yeah.
that we evaluate that one, it gave us it could give us two listing like C star and D star.
Oh.
Is there any similarities between this and
So alpha beta, the random linear combination, that's just one trick. There are two ways to do it.
okay.
So there's this one, this alpha beta one,
Yeah,
and then there's that line one.
line.
Yeah. So if you are using the alpha beta one, you're not going to use the line one. Yes. So there are two ways of doing the same thing. Alpha beta. It's simpler to.
Is there any similarity?
They are both trying to
They are achieving-
merge.
I know
They are achieving the same
They
thing.
will achieve the same goal, but do you use the idea from that line
On a philosophical level. So that before we can even start talking about that, you probably need to understand how alpha beta works, and then you need to understand how the line one works. Then you can now start like reasoning about the similarities. Yeah. Okay.
Yeah.
So now we're back. We're exactly where we were with W0, right? At the point we had W0 of what R1 is equal to M0. We're exactly there. So all we just need to do is just repeat everything we have done so far. So this is giving like for loop vibe. For loop, do stuff, merge, then go back again. Do stuff, two, merge, then go back again. On and on like that. Is that?
The initial one.
Yeah, the initial one was already 1. Okay. So, quick run through. This is now the claimed sum, right? So O3 is the claimed sum of F1 evaluated at R3 BC, right? Which is something like the claimed sum evaluated at F1 BC, where we have already partially evaluated R3. This makes sense?
Yes.
Then now, we can now run some check. Yes, again. So we'll run some check on this F1 BC. That'll be our initial polynomial. Then O3 is going to be our claimed sum. So at the end of the day, we'll have oracle check. The oracle check is going to be on F1 BC. So instead of B, it will be like R1, R2 is equal to some value, let's say C7, right? The verifier still cannot evaluate this by itself because this depends on W2, which it does not have. So it will have the add R plus the mul R, but it's not going to have the other ones. So the prover now has to give it the evaluation of W2 at what? R1. I don't know if I'm just black boxing them, right? That's called it's like 004 and W2 at um right? Then you do something similar. You now do like 04 plus 05, then you do 04 times 05, then you get a value. This value hopefully is equal to C7 so that the oracle check can be completed. But then we're giving something that you still don't trust, right? Is equal to 04 and W2 of R2 is equal to 05. You don't trust this. But now you have gone closer to your input. You started at W0 and now you're at W2. So the last one that you're going to do will not have exactly the same thing, but on W3, which is what you already have. So you do the merge, then you get something on W2 of what? R3 is equal to 09, right?
No, sorry. No. Is it plus? Add R plus or multiply? Add R plus or R plus?
Thank you. Yeah. So now you have W2 of R3 is equal to 09. You're back. Yes. So now, eh? How do you what?
Aren't they supposed to be 4 claims on it?
No, because we merged these two. You know, if we had not merged, this one would have given us 2, and that one would have given us 2. But we merged it into one first, before we now continued. So this one will now give us just 2, 2. Oh, yeah, no, you're talking about W2, right? It should be R1, R2.
No, that part you're filling up for. Why in B and C, wasn't it supposed to be
4, are we?
Yeah.
Yeah, supposed to increase to 4. I just wrote it like that. Yeah, I'm just assuming that B can be decomposed into B1, B2. So it depends on the.
So I got to the point where you use the 2 to 1 trick to get
W1, R3,
on the W1 and the
O3.
so then what is going to
It's similar,
Just skip from
right? O3 is going to be what? The claimed sum, right?
yeah.
Of a sum check.
Yeah.
This sum check is going to be the F1 now, right? Which is using W2 under the hood, right?
Yeah.
So that way you can reduce a claim about W1 to a claim about W2, right? So that thing that looks like triangle with trailing dots, that's sum check. Okay? So we run sum check on this. And at the end of the day, we're going to get an oracle check. Which is not. Wait, I'm coming. We get an oracle check,
Yeah.
right? But the verifier cannot evaluate F1.
Yeah. Because depending on W2.
Exactly. So the prover now tells you what W2 evaluated at R1 is and what W2 evaluated at R2 is. Then that way the prover can now evaluate the F1, the verifier, sorry. Right?
Yeah.
And then it gets a value. And the hope is that that value is also equal to the what the claimed sum was supposed to be. And then if it's equal, it's done with that round. But then he had 2 things that he didn't trust. Then we merge those 2 things into one again, and then we repeat.
So let's go. Okay, so for W zero on the bottom right, it says it's going to be equals to M0.
Wait, for what?
Bottom right.
Is it this?
Yes.
Okay.
It says W0 is going to be equal to M0.
Yes.
Okay, let's say something like W1 at is it how it's now? It's
What about R, right?
just about like we always evaluate to a clean sum.
Yes. Because of you can always represent any W at the top as a sum of the W's at the bottom.
So, like, do you know, I'm just thinking about it now. We have objectives,
Yes.
right? So something like a W might have more than one variable.
Yeah. Even the W2 has more than one variable.
Yeah.
I was one that just wrote it like this.
But we are evaluating that only one.
It was me. That was my fault. In the sense that when you run some check, this thing here is no longer like BC, right? It's B1, B2, C1, C2. I just black boxes it that you should just know that C might be able to like decompose into. So when you now run some check, right? You're not going to get an oracle check that is actually in terms of R1, R2, R3, R4, right? That's supposed to be equal to C7. So what the prover is going to give you is not just W2 of R1, it's going to be W2 of R1, R2, and it's going to be W2 of exactly. But then everything is still exactly the same. So it's not like you are then you merge it into one.
So the final one is still going to have two
Yeah, we don't have two sum checks. We have just one sum check. But then that one sum check is over a polynomial that maybe has more than. But sum check doesn't care how many variables your polynomial has.
Okay.
I'm trying to understand your label. 6, 7.
Just forget the label.
No, it's 6.
It's not 6. It's just a label. It's just that's supposed to be the output of the oracle check. You get. But I'm not tracking. I just did not want to write something I've written before, so I just wrote something.
Does this mean that you are only evaluating for one gate in a layer?
How?
Because you're only doing like add. I mean, this option is for a gate now.
Which one? Is it this?
Yeah. Not for a gate, like left and right for a gate. For you for a layer.
This?
Yes.
So the thing now is that technically it's kind of like that. Like once you have chosen your R's, then it's like you're already fixing it to like a particular. It's no longer a gate anymore because we have left like the Boolean space, right? It's now like R's.
You know, there's one point where you had like maybe one layer that went like I think 3 plus and then one plus. At one point, I will like have multiple like that plus. Maybe like even I think like inside the other.
So the way you guys think about this thing is that your circuit can be converted into polynomials, right? Once they have been converted into polynomials, you can now use them for anything that you want to do. You can now devoid them of lots of like their circuits meaning per se. So when you're evaluating over like random points, it's no longer like there's no gate at R1 or there's no gate at R2. There's no left node that has R1, R2 as the labels, right? This one now you're not dealing with like polynomial identity testing. That's that the left side should be equal to the right side. But I don't want you to know where I'm going to check it at. That's why I'm now like giving you random points that I sample from the field to check at. It's only when you're looking at it in terms of like zeros and ones, that's when it still has like a relation to the actual gate circuit diagram. You get. But it will get clearer over time. Okay?
You said this and
Field elements, yes.
But I thought they were like the Lagrange basis that evaluates 0 and 1 depending on whatever you're checking.
It evaluates 0 or 1 if the thing you evaluate it at is in the Boolean space.
Oh, okay.
But then we're checking it at R1, R2, blah, blah, blah. So fields. So the output 2 will also come from the field. Yeah.
but the other one that's not would still evaluate to 0.
It might not.
Wow.
For something to evaluate to 0 is like you're saying that something should be like 1 minus x, right? If you evaluate at 0, you're going to get 1, right? If you evaluate at 1, you're going to get 0. Bless you. But then you can evaluate at any random field element, also like 4.
Okay.
You're going to get minus 3. And if you evaluate x at 4, you're going to get 4. So these two things are already like non-0 and 1. So when you multiply it, it's already like minus 12.
And it doesn't like, it still works.
It's a multilinear extension.
Let's continue.
So we're technically done now, right? But let's finish for the W2.
Yeah.
I'm just thinking like
Okay, let's finish to W3. Then we'll just like open it to full blown ask. Eh? 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 This an example will be crazy.
Let's
It's a
do
bit-
example. Actual
I think you
example.
should make it very small.
A very small circuit.
Just like two layers.
I don't know, no worry. You guys will buy me food, sure. So okay. So this W2 of R5, R6, we have merged it, right? So we got one thing. Now this 0, 9 is a claim sum. So 0, 9 is supposed to be equal to the summation
Sorry,
of...
very school.
Yeah, I want to write it.
Oh,
You shared this also.
yes. I shared the last one. So I'll share this one. Let me know when I should continue. Okay, let's continue. So this can be related as a summation of the layer underneath, right? So this is going to be F3 of is it F3? No, F2 of now A is 2 bits. That's R5, R6, right? Then B, I can't remember what B was. What is B for W3?
You're saying A is 2 bits.
Yeah, I'm looking at in terms of like W2, right? We're doing W2 to W3.
Yeah.
So A is 2 bits, but then B and C are 3 bits
No,
each.
a field are passing. There isn't a field.
Yeah, but still, each bit will be turned into a field element. Like the function signature doesn't depend on whether it's a bit or a field. It just depends on like this 1 1 now will be replaced with one field element and another field element.
Which one?
This 1 1.
Okay.
Do you understand? Like see now. This is what our add and our more looks like. 2 for A, 3 for B, and 3 for C. Whether bit or field. Do you get? Final signature is fixed. It is well. It is well. So we have B1, B2, B3, C1, C2, C3. Cool? So we're going to be summing B1 all the way to C3 from 0, 1 raised to the power of something. It's always like this is 1, 2, 3, 4, 5, 6 raised to the power of 6, right? So this one has already been partially evaluated. Yes, 6. Yes. because we have 6 bits now, right? 1, 2, 3, 4, 5, 6. So it will be 0, 0, 0, 0, 0, 0, 0. Then 1, 1, 1, 1, 1.
That's the formula, that would be like 2. Like you write 2.
Oh, that does depending on the layer. Eh. Good luck. So we good? Now this F2, it depends on W3. So now this is the last layer. Cool. So what we're going to do now is this is a sum check equation. We defer it to the sum check guy. Sum check guy will do his thing. By the end of the day, we're going to have oracle check. Now this one is partially evaluated. I'm going to remove them now. So it's supposed to evaluate at R1, R2, R3, R4, R5, R6, right? And the answer is supposed to be equal to C, let's say C8, right? Verifier now can fully evaluate this F2 because F2 depends on W3 and the verifier has W3. The verifier also has the add I and the mul I, right? So the verifier will be able to do add 2, right, to get add R, right? It will be able to do mul 2 to get mul R, right? And then it's supposed to do W3 of what? R1, R2, R3. And it's supposed to be able to do W3 of R4, R5, R6. Remember that it's always split in half. Like this is the B and this is the C. And the verifier has W3, so it knows how to do this. So it's going to get, let's say, O10, O11. Now this one was not given to him by the prover. This one was computed from what is trusted. So when you now do the if the answer is now equal to C8, which is equal to what the oracle checked, then everything that has been done so far is considered valid. And then it can now accept that initial W0 of A that was sent as truth.
Now this C8.
Yes.
Like I'm trying to see because now we're about to do this.
Yeah.
Can we like compare each of those inputs?
So this
Some
same
of
with
the values
those
that are getting.
Can we compare?
The inputs, for example, the input 1, 2, 3, 4, 5, 6, 7. Now, how do you compare that? Like apart from this one, do you get actual values that you now see that so it's originally this? I don't know if you understand.
No. You
That
don't.
was the only point that we're trying to double it down to get this 1, 2, 3, 4, 5, 6 somehow.
Yes, kind of, but how do I put it? The point is that when you get to this last oracle check, you can do it trustlessly. That's the point.
Because now you know your W1 and W2.
You know your W3.
So the W, yeah, the W2. Prover is going to give you.
It's not, yes. Before you couldn't know this yourself.
Oh.
So the prover had to give it to you. Every time we're done with the round, we always had something pending that was not trusted. And we had to do over and over again. But now this W3 is the input itself. So the verifier can get this O10 and O11 in a trustless manner. It doesn't have to trust the prover to get that. And because of that, once we're now done with the oracle check, there is no pending, unverified
Okay, I think I get it.
claim.
That's the big
Yes. The input. Huh?
Just or should be 6.
No, W3 is a 3-variable polynomial, I believe. So see, A1, A2, A3, right? So we're supposed to evaluate at the left, and we're supposed to evaluate at the right. That's what this is doing. This is like B. And this is like
instead of now doing it, so that means that okay. How do we do now? If you value that 0, 0, 1,
Yes, it
Getting all
still
those
gets, yeah,
points.
it's still the same
that's
polynomial.
another way
That's not another way to check it out.
to check it.
No, the W was not given to you. You always had it. So you checking that your W3 is correct does not really
I always
say
had
anything.
it.
Yeah, the verifier always had W3. That's the input.
Polynomial form.
Yes, that's the input. The verifier knows the input to the circuit, just does not want to do the work of like moving the input forward to get the output.
Sorry, this W3 that we know, is it the same thing as like trusted circuit? It's the input. I know it's the input, like I just want to know.
No,
How is it very
very
different?
different thing, yeah. We should do an example, are we?
Yes.
Sorry, I'm just confused.
Confirm.
To the circuit.
Ah,
Yes.
2 layers,
Just 3 gates.
3 gates, 2 layers, 3 gates. Okay, we can do that actually, I'm sure. But it might not be interesting. In the sense that we might not see any. Can't even do this thing.
Why?
Come, we have to do alpha, beta.
Let's use
No, we can do 2 sum checks. And
No,
we'll
we can't.
do,
Don't let us do something.
we'll do 2 sum checks. We'll do
You
it 2
don't
sum
have
checks.
to alpha beta is good.
Oh yeah, what do you say? I say something. In evaluation form. Sum check verifies that if you sum a polynomial over the Boolean hypercube, it will give you a particular sum, right? The way it does that is that it verifies some round poly checks, right? 0, evaluation at 0 plus evaluation at 1 is equal to a certain value. And then finally it does like an oracle check to verify. So it does a series of round checks plus a final oracle check. The problem now is that to do that oracle check, you need to evaluate the initial poly at the randomness, at the challenges. But the problem now is that in this model, the verifier does not have the initial poly. So the verifier cannot complete the sum check process because it cannot do that oracle check by itself without help from the prover. So the prover will help. The prover will help, and then it will be done with the oracle check. But then, because of the prover help, there are things that it doesn't trust yet. So it has to continue this process until it gets to the point where it can verify that oracle check without any help from the prover, which is why that's when it now ends. It's used to prove that a circuit was evaluated correctly. This circuit, it's used to prove that all the intermediate steps were done correctly. And a circuit represents a problem. A program. Yes.
So the circuit does not like is not limited to GKR and ZK. Is it?
What did you say?
This kind of
It's not limited to GK. It's not limited to GK. It just represents a computation. Up, down.
So now we're like 90%.
Yeah, now you guys are like, yeah, like 85%.
You say that's it.
Yeah.
That's the class.
The theory. Huh?
Oh,
Oh, more.
Relax now.
Yeah, just 2 to 1 trick left.
And that's just the theory.
Yeah.
This is proving now, people.
Yes. No. Oh, how do you verify?
This is
This everything. This is interactive GKR.
Yeah.
Oh, there's no reality.
Yes.
Ah.
You are not implementing interactive GKR.
Ah.
What you're implementing is non-interactive GKR. So every time you sample randomness, every time that it says randomness, it's transcript.
so how about we use Fiasha?
You'll see it's reaction, right? So anytime that the prover, like that time the prover is sending W0 and it's sending W0, writing into the transcript. The time the verifier sends R, yeah, absorbing from the transcript. It's not hard to convert non-interactive to interactive. Which polynomial? The initial polynomial is no, you're not sending initial polynomial. That's like the f, those FBCs. You're not sending those. You're only sending like the round, but you don't need to do all those. You modify your sum check to already do that part of it. The code is not crazy. No, it is crazy actually. It is crazy.
This all of some shit.
All of GKR?
Okay.
No.
Where is
There's theory and implementation. You are like 85% done with theory.
Where is the meaning sense?
It's in the alphabet. Yeah. And then creating like a neat mental model. That's what I'm putting as 15%. A neat mental model of the entire process. It's rough right now. So you guys will need to like go over this thing again until everything is just like clear. When you can see everything, you should be able to describe the GKR process in a couple lines. Like I was talking about, it should be a couple lines, succinct, exactly. But right now it's going to be all over the place. Then after that, there's now the implementation. Yes, implementation is going to be. You guys still have a lot to do there. Any error you see might be coming from your sum check, or your GKR, or your polynomial.
You said something about we having like a partial sum check. So I guess I have to implement that in our sum check. No, I'm not changing the sum check, I'm just adding.
So, like in my sum check now, I have two methods, right? I have prove, and I have prove partial. So prove is still doing like the regular sum check with the initial poly and everything. And prove partial is doing the sum check, but it's not adding like the initial poly to the proof. Wait till. After I finish our example. Let's attempt an example.
Okay.
You guys should describe a circuit for the example.
Okay.
How many layers?
2 layers. 3 layers.
2 layers.
It's you that will come and do this one. I'll just direct you. So you have input here, right? This is too easy. That's the problem. Now we only have one FBC polynomial. Okay, no, we have 2.
Yeah, we have
Okay, I think it's fine. Yeah, it's fine. I wanted to make sure that the prover sends something that we don't trust. Okay. So now, let's assume this is plus, times. Alright? We good? Now let's put 1, 2. If we feed forward, what is it? Right? This is what we'll figure out how the W0 should be. Whether it should be like just 14 or whether it should be 14 and 0. Yeah. So let's assume that it's just 14 initially, right? So W0 does not have any variable, it's just 14. Then W1 is going to be what? What's the polynomial for this? 1 minus a times 2 plus 12a, right?
Yeah. Can you write the leader 0 and 1?
Yeah. Right? So this is what 2 plus 10a, right?
Yeah.
So this is W1 of now W2, it's going to be AB, right? It's going to be equal to 1 minus A, 1 minus B, times 1, right? 1 minus A, B,
minus
3, right? Let's simplify. This was 1, right?
Yes.
This is correct, right?
2B minus 1. 2. Why give you everything?
No.
3.
Just confirm whether we're correct. Right? Collect like terms. Constant. Is there another constant? No. Then minus B. Is there any other thing that has just B?
Plus 2B.
Is there another thing that has just B? Minus A. Is there another thing that has just A?
Plus 2A.
Is there another thing that has just...
AB cancels out.
Right? So constant will remain. And this will be what? B, right?
Plus 2.
Plus 2A. Then this one disappears. This is 1 minus 2 minus 3 plus 4. Right?
That's 1 minus 0.
This is 0.
0.
Yeah, 0.
1 minus
4 plus 1 is
5.
5. So this is what our W2 polynomial reduces to. So let's just write it out. Huh? So W1 is equal to 14. No, W0 is equal to 14, right? And W1 of A is equal to, it feels so weird that there's no, but yeah, let's just continue. 2 plus 10A, right? Then W2 of AB is equal to 1 plus B plus 2A. So these are our W polynomials. Now let's build our add and moles. Let's start with add 0. What's the function signature? 0, A, B, C, right? The only thing that will make this evaluate to 1 is when A is 0, B is 0, and C is 1, right? So that's A should be what? 0, 0, 1. A should be 0, that's 1 minus A, 1 minus B, C, right? We simplify it as 1 minus B minus A plus AB. Then you can just put C everywhere.
Bro, I don't understand.
Yeah, please, can you start this page?
So we're doing the add for the layer 0, the output layer, right? The only input that will go into that function that will give you 1 is 0, 0, 1, right? So that means A has to be 0. That's 1 minus A. B has to be 0, 1 minus B, and C is just C, right? What do you mean you don't get?
We are doing add 0 for,
Just like Lagrange.
for ABC.
So
Which add not are you doing?
add node is the add MLE for the
For that
0 layer. That's what the 0 is for. I know the add is like the output, left, right?
Yes.
So the only time this will vary to 0 is to 1 is when the output is 0, left is 0, and right is 1. Makes sense? So if it's 0, 0, 1, then to check that A is 0, you do 1 minus A. To check that B is 0, you do 1 minus B. And to check that C is 0, you do C. That's check 0, check 1. Cool?
Yeah.
Cool to you. Cool?
This is the only one you do.
That's the only thing that can give you 1. for the add 0 because there's only one add gate on that layer. The rest of them will be multiplied by 0, so we don't need to
So
do
if
those.
there's 1 1 1, that'll just be
If it's a 1 1 1, that will be ABC.
Trying to get the polynomial.
and in this case your C is the your A is the output.
Yes. Is there any simplification here? I don't think there's any simplification here. So we really need to make sure that this is correct. Did any other person confirm this?
We can just like put C outside that so that
Which one is correct?
It's fine, it's fine, it's fine.
Correct.
Then what of mole 0?
0, 0, 0, 0.
So there's nothing here, just 0. Right?
Yes.
So we have our add and our mole for layer 0. And let's get our add and our mole for layer 1. So that's add 1. How many bits? A is 0, A is 1, then B, C, 2 each. So this is A, B1, B2, C1, C2. What input to make the add 1? That's 0, 0. No. There's nothing.
Is it add that be more? Is it add that be?
Okay, add 0.
When you get 2, are we doing add? Okay, that's 0. That's more.
Now mole is also the same, right? Now we have two inputs, right? 0, 0, 0, 0, 1. So one of them is 0, 0, 0, 0, 1. While the other one is 1, 1, or 2 ones, and okay. Yes, and we'll sum the result. Okay, so that means this mole I is now either this one or this one will make me evaluate to 1, right? So that's the summation. So, oh my god. We don't even need to do this thing fully. This is what we were doing last time too. Right? Then plus. This is our mole 1 polynomial. Okay? There is no add 2 and there is no mole 2 because that's the input layer. So we have all our polynomial ingredients to start proving. Make sense?
So is that plus?
Yes.
This right? Yes, plus. Are we good? Can we proceed? So the prover sends W0. This is where we'll know whether it's supposed to be 14 or 14x. Let's start.
14A.
Or 14. I don't know whether it's going to be. If it's like 0, it will be like 1 minus a, right? Times 14. Which will be 14 minus 14a. So this is another candidate for like the W0. But also try it with just 14 and see if that works. Then if it doesn't work, I have to find an explanation for why it doesn't work. Okay. So the prover sends what? Right? Which is equal to what? 14. Just a constant.
Yeah.
It's weird. Because then regardless of the R that the verifier chooses, the answer is always the same. Which is, well, we'll see. So let's say the verifier now samples R. Let's say R is 5, right? 5 was sampled from the field. Now we need to get our M0 evaluated at. So what we're saying now is that give me a sec. Okay, so the claim now is that W0 evaluated at 5, right? So that means this 14 is serving as our claimed sum.
14 is our
Alright? So there is another way to write the evaluation of W0 based on the sum of. Make sense? So 14 is actually equal to the sum of F. Now what is R? Then B, C. Right? Is it 1 bit? Okay, it's 1 bit. Now we will need to run some check on this. But before we do that, let's get our F0 polynomial so that we can partially evaluate it at 5 before we now do some check. This is where the work now starts. F0 of ABC is equal to what? Add 0, right?
Yeah.
Of ABC times W1 of B plus W1 of C, right? Then plus cool. Now let's get our let us get our add 0. Where's our add 0 again? Add 0 is this thing here. Does someone have this written down?
Yes.
Okay, just tell me.
C minus BC minus AC plus ABC.
Right?
Yeah.
Then we're multiplying this with what's W1 of B? What's W1? That's W1. The W1. 2 plus 10A. 2 plus 10A.
We have polynomial. Okay.
The polynomial is 2 plus 10A, right?
Oh, yes. Polynomial is 3, sorry. Yes.
Right?
Where is 5?
Yeah, I'm doing it generically first. Then I'll now.
Yes, W1 of B is 2 plus 10.
Record part 2.
Yes, sir.
You see? The Google Meet.
What's up for part 2?
Google Meet just stopped sharing right now. And now the OBS is stuck.